Based in Northamptonshire in the United Kingdom, Scott Bader is a unique organisation employing more than 650 people worldwide. It is a leader in unsaturated polyester resin technology, supplying its Cristic brand resins and related products in over 90 countries. Scott Bader first introduced unsaturated polyesters into Europe in 1946. The resins had to be cured in the absence of air using closed moulds in the Marco process. Intense development rapidly led to the introduction of products that cured in open moulds, making possible the contact moulding processes which today dominate many parts of the composites industry. In these processes, either brush or spray technology can be employed in the application of the polyester gel coat and backing laminate. Open mould processing has been particularly adaptable for manufacturing composite components of all shapes, sizes and complexity. These components have been used in many applications within the marine, land transport, chemical containment, building and construction markets. So why are moulding companies turning full circle and starting to investigate closed mould processing again? There are a number of commercial and environmental pressures which are driving moulders to adopt alternatives to hand and spray layup. Improved product quality, improved product consistency, improved productivity, reduced VOC emissions, and reduced labour costs. It is for these reasons that GRP moulders have started to use closed mould processing for a number of applications in more recent years. This is particularly true in the land transport industry, but is now growing into other areas as well. Scott Bader is dedicated to the development of closed mould processing and is able to provide expertise and materials for a range of these techniques: vacuum injection, VacFlow, RTM Light, resin transfer moulding, Cristic Impreg LPMC, and Cristic SMC. To support the development of closed mould processing into the composites industry, Scott Bader has created a centre of excellence at its headquarters in the UK. The basic principle of vacuum injection is to inject resin through dry reinforcement placed between a rigid airtight mould and a flexible film. Vacuum injection can offer distinct advantages to moulders. There is minimal capital investment. Existing moulds from hand or spray layup can be used. It is adaptable to a range of components of different sizes. Physical properties are improved due to the compression effect from the vacuum. Changes in component design can be incorporated easily. Reinforcement is loaded onto a gel-coated mould. The mould can be a modified layup mould. Core materials can be easily accommodated, but the moulder should ensure that resin can flow around them and that care is taken over their accuracy and placement in the mould. A galvanized metal coil can be used to create a peripheral channel. If a new mould is made, then this channel can be built into the mould flange. Plastic T-pieces are used to allow easy tube connection. Vacuum bagging tape is placed around the mould. The flange should be free of glass fibres, which may create a leak through the tape. A plastic mesh can be used to aid resin take-up at the end of injection, or be used as a gate to distribute the resin quicker across the mould surface. Use of peel ply allows easy removal of this mesh after demoulding. The key to vacuum injection is a textured film which allows excellent resin distribution with no additional layers over the laminate. The moulder should ensure that there is enough film to take the shape of the moulding. Up to 50% more film than moulding area may be required. The film is sealed carefully using the tape. Pleats are used to ensure that there is no bridging of the film. A vacuum is applied and the film checked for leaks. Finally, the film is slit and a tube attached in the center. Resin is fed from the outside tube into the peripheral channel with a vacuum of between 0.6 and 0.8 bar being pulled from the central point. This method has the advantage of quicker fill times, but the disadvantage of a greater risk of drawing air across the laminate if the bag is not sealed properly. An alternative is to feed the resin via the central hose connection and pull the vacuum from the outer channel. When full, the resin inlet is clamped. Some resin is pulled into the outlet catchpot to ensure a full air-free component. This outlet can then either be clamped or the vacuum slowly reduced to a holding level of approximately 0.3 bar. The mold must be held under vacuum until the resin has gelled. Once sufficient cure is attained, the mold is stripped. The part is demolded and then trimmed. However, there are certain limitations on the use of vacuum injection. The setup and preparation time can be significant. Ensuring a vacuum-tight setup can take time. The cost of disposables can be significant, and there is a loss of laminate thickness due to the compression effect. But vacuum injection is a versatile process which can be adapted to much larger components, such as this dinghy of 10 square meters. However, the principles of the process remain the same. Care in accurate and consistent preparation is the key. The VacFlow process utilizes lightweight, matched GRP tooling and resin injection by vacuum. There are several advantages to VacFlow: low capital investment, a reusable upper tool, improved productivity over contact molding techniques, and 2 molded surfaces. The molds for VacFlow are constructed from polyester GRP. The lower half is of a typical hand layup mold construction with a wider and stiffened flange area. In VacFlow, gel coat is applied as normal by hand or spray machine. Surfacing veils can be used to reduce fiber print-through. The main reinforcement is then placed in the mold, ensuring no gaps between it and the gel coat. The advantages of deformable stitched mats, such as Schomer's Rovicor, can be seen. These dramatically reduce glass loading times. If core materials are incorporated, accuracy of size and care with placement into the mold are crucial. When joining 2 pieces of reinforcement, a slight overlap is necessary, ensuring no resin-rich or reinforcement-rich areas which may lead to poor flow or difficulties with mold closure. Woven reinforcements can be incorporated to give extra strength. Benefits may also be seen from using combination fabrics such as Schomer's Rovimat, where the layer of chopped strands can help resin flow and also reduce print-through. A lightweight polyester GRP upper mold is then placed onto the reinforcement. The resin inlet and vacuum takeoff tubes are attached. A catchpot is used to ensure excess resin does not enter the vacuum pump. A full vacuum is pulled between the 2 seals to clamp the mold, and a second vacuum of 0.6 bar is drawn from the central point. The resin is then catalyzed and introduced to the mold via the resin inlet tube. The resin travels quickly around the peripheral channel and then starts to flow through the reinforcement. Injection of this component, which has a developed area of 2 square meters, takes between 10 and 15 minutes, depending on choice of resin and reinforcement. Once full, the resin injection is stopped by clamping the inlet tube. The central tube is then clamped or the vacuum released to a holding level of 0.3 bar. It is essential that this vacuum is not released until the resin has gelled, otherwise the tool will relax and air will be drawn into the laminate. Once sufficient cure has been achieved, the tubes are removed and the upper mold lifted to allow demolding. The gel-coated GRP component with a molded back face can then be removed. The vac flow process does have some limitations. It is an ambient temperature process which restricts cycle times and process control. It is necessary to manipulate an upper tool. It requires larger dimensional tolerances than RTM. It gives reduced flow rates compared with RTM and RTM Lite. The detail and accuracy of the upper mold design is critical to the success of vac flow. A lightweight gel-coated GRP laminate using a more flexible resin system is ideal. Simple inserts can be used for the resin inlet, the central takeoff port, and the main vacuum clamping port between the double seal arrangement. The primary inner seal is of silicon rubber to ensure maximum resistance to styrene. The outer seal is of neoprene rubber and is extruded as a wing profile. This ensures easier mold closure and clamping. Once closed, a reusable metal catch pot can be inserted into the central takeoff port to collect any excess resin. The vacuum takeoff points can be attached to the vacuum pump, which can either be an air-driven Venturi pump, such as the Vacuum Minder, or a mechanical pump with a split reservoir. The resin inlet tube is then inserted, connecting the mold to the resin source. The vac flow process offers many benefits to molders and remains a cost-effective entry into closed mold processing. RTM Lite is an extension of the vac flow process, using an injection machine to introduce the resin into the mold. It uses the same mold design as vac flow. RTM Lite offers advantages to the molder. It has a reusable upper tool. It can use existing vac flow molds. It offers improved productivity through increased flow rates. It gives two molded surfaces, and it allows control over resin injection. The mold is gel-coated, the reinforcement is placed in the mold, and the tool closed. The mold is clamped by drawing full vacuum between the double seal. At the central takeoff point, a vacuum of 0.6 bar is drawn. However, in RTM Lite, an injection machine is connected to the resin inlet port. A predetermined number of shots is then injected into the cavity at around 1 bar injection pressure. Care must be taken not to inject at higher pressures, which will distort the molds. The resin flows around the peripheral channel and is then drawn to the central takeoff point. Once injection is complete, after about 6 to 7 minutes on this 2 square meter component, the resin inlet is clamped, and then the vacuum at the central takeoff point is reduced and clamped. As with vac flow, it is crucial that this vacuum must not be released until the resin has gelled. Once cured, the part can be demolded. There are some limitations to the process. RTM Lite remains an ambient temperature process. The cost of an injection machine. Injection pressures are limited compared with RTM. But RTM Lite can offer the advantages of vac flow along with further process control through resin injection. The basic RTM process involves injecting a resin through reinforcement placed in more substantial rigid tooling manufactured from composites or metal. RTM can offer distinct advantages, particularly if temperature-controlled tooling is used. Increased productivity through the use of higher injection pressures and heated molds. Improved quality. Improved product consistency due to better process control. Improved dimensional tolerances. The mold is gel-coated by either hand or spray application. Because of the use of heated tooling, the reinforcement can be laid onto the gel coat far quicker than at ambient temperatures. A surfacing veil or fleece material, as shown here, can be used to reduce the glass print-through. Once again, deformable stitched mats, such as Rovicor, offer distinct advantages in glass loading. Core materials may be incorporated, but their dimensional accuracy is critical to the success of RTM. The mold is closed and clamped using bolts, toggle clamps, or sometimes a press. Liquid heating is used to ensure consistent temperatures. 40 degrees C is a typical mold temperature. The mold is vented at the point of final fill. Resin is injected from a central point at typical injection pressures of between 2 and 4 bar. Machine options such as the mold pressure guard, or MPG, ensure that the injection is controlled and that the molds are not overpressurized. It would be expected to see a small amount of resin at the vents to ensure that the mold is full. Once injection has been completed, the injection head is removed, a stopper is placed in the injection hole, and the machine flushed with solvent. Once the resin has cured, the mold is opened and lifted to allow demolding. The heated tooling allows quicker curing of the resin, and so quicker cycle times are achievable when compared with ambient temperature processes. RTM can use metal molds such as nickel shell, aluminium, or steel for maximum durability and improved surface finish. However, the principles of the mold design and the process remain the same. Further automation can be achieved using autosprue technology. This valve is built into the mold and allows simple connection of the injection machine. At the end of injection, the autosprue automatically flushes the machine with solvent, and then the machine can be easily disconnected. Once the part has cured, then it can be demolded, leaving the mold ready for the next component. The use of RTM can be limited by the higher cost of tooling, the cost of an injection machine, but also by the gel time required for mold filling, which limits productivity in very high volume applications. However, RTM is now a proven technology for fast and efficient production of GRP components. To complement the range of liquid molding techniques, Scott Bader also supplies a full range of Cristic Impreg low-pressure molding compounds and Cristic SMCs. These thermoset compounds molded under pressure offer fast cycle times and a more automated process for high-volume composite applications. Scott Bader is dedicated to providing materials and expertise for a range of closed mold processes. Vacuum injection, a simple and adaptable process using a flexible film and traditional GRP molds. VacFlow, a cost-effective entry into closed mold processing using lightweight and matched GRP molds and injection by vacuum. RTM Light, an extension to VacFlow using vacuum-assisted resin injection to further control the process. RTM, a fast and efficient method for producing GRP parts using rigid matched molds and controlled resin injection. Cristic Impreg and SMC, a full range of molding compounds for fast, efficient and cost-effective molding of GRP parts. Scott Bader's promise is to offer excellence of product and excellence of service for all composite applications. Scott Bader is committed to serving its customers not just today, but as a reactive, reliable and independent business partner working together for a better tomorrow.